because it's more relying on the knowledge, and the models have all the knowledge to solve them.
Right.
Yeah, that's a one follow-up. Yeah. The other follow-ups, right? So one thing very interesting to us is like uh, so we're solving problems. Can it be used to propose problems? Yeah, so that's also related to like can AI models be used to propose sensible research questions, right? So
Yeah.
research open questions. So if that is the case, then it can self-propose and solve, and then that's a flywheel, and it's gonna be a big contribution to the entire research community.
Welcome to Manifold. My guest today is Professor Lin Yang of UCLA. I invited him to be on the show because I noticed some very interesting research he did with a collaborator in which he used off-the-shelf frontier AI models, such as Gemini 2.5, to solve 5 out of 6 problems on the International Math Olympiad, which was just held over the summer. And those problems had not been seen probably by any of the models in their training. So this was a true test of their Olympiad problem-solving ability. And Lin and his collaborator were able to build a pipeline which uses ordinary off-the-shelf models, but which are capable of solving problems at that level of difficulty, at the level of a human gold medalist at the IMO. So Lin, welcome to the show.
Thanks, Steve, for the invitation. It's my great pleasure to be in Manifold.
Great. Let's talk a little bit about your background. So you have 2 PhDs from Johns Hopkins University, one in physics and one in computer science.
Yeah, that's correct.
Yeah, and you did your undergrad, I think your undergrad degree is from Tsinghua University.
Yeah.
In both math and physics, is that correct?
Yeah, there's a program. It's called Math and Physics, Basic Science and Experimental Program, something like that.
Great.
Yeah, yeah.
So tell us a little bit about your background. Where are you from in China? What did you want to do when you were 20 years old?
Oh, okay. I was born in a village in southern China. The city is called Guilin. It's a part of Guilin. It's a small village. I'm not sure you've heard about Guinea. It's famous of its mountains and waters. Yeah,
I know very well what Guilin looks like
yeah,
from the famous paintings and photographs.
yeah.
I've never been there because I had a
Mm,
chance to go there a long time ago, but I decided, well, it's a long story. I'll tell you about it
yeah,
later. I've
yeah,
never actually been there, but it's quite a famous place.
yeah. Of course, the province is pretty poor. Well, I mean, at least at the time I was born and I was growing up, right? So we don't have very good education there. Somehow I went to this top university and Tsinghua University right after the national exam. I think I was pretty happy about it, excited about it, and so when I was young, and the only information I get is that you should be a scientist in the future, like someone like Einstein, someone like the big names, right? So in physics, so that's why I chose physics to study. And well, at undergrad school, Tsinghua. I'm still a big fan of physics, right? So I'm have a big dream of winning Nobel Prize someday. So then I got super excited about astronomy and cosmology. At the time, actually, I was doing high energy astrophysics during undergrad study. So I was using this Hubble telescope data, and there's another X-ray telescope data. It's actually Changer. It's called Changer, I think. X-ray telescope, and to find these black holes behind this Hubble telescope images. So it's pretty exciting. So then, because of this work, and of course, my GPA was not bad. It's okay. So I got into Johns Hopkins, which has a big team in astrophysics, right? So, and Johns Hopkins is pretty famous for that. So I went there and then started to do astrophysics with my advisor there, who is actually Alex Selle, Professor Alex Selle. We're actually trying to study dark matter. So, but studying dark matter, I mean, a little background, right? So we don't know what dark matter is, but the assumption is that dark matter consists of 70%, about 70%, 75, right? So of the matter is in the universe, uh, which some unknown matter. But in order to study that, we have to do a lot of simulation because you cannot actually capture them. Until now, we don't capture any particles that is really a dark matter candidate, right? So we have to do a lot of simulation, and so we have to do the supercomputer simulations on large data set. And after we got this data set, we have to do a lot of analysis, right, in order to find the signals. So that's why I got into this using GPUs to coding on this dark matters. And it turns out that during the time I was doing the physics research, the majority of the time I was doing coding and debugging. So then, okay, so I said, okay, I'm doing too much in the algorithms. Maybe I should do a master degree in CS as well. So I just go there and take a bunch of courses and actually my CSO advisor there, I found his research is pretty interesting, and whose name is Vladimir Brivelman. And he's actually doing computer science theory. It's very theoretical. Like you need to prove this, prove that. So that's very interesting. But given that I already have some math background in undergrad, right? So it's I got into that field pretty quickly. So I actually started to solve their problems. And the Vova actually we call my advisor Vova. Vova is also was also pretty excited about my ability. He was suggesting to me that why don't you do a PhD degree with me as well? And the lucky thing is that he and my physics advisor, they are good friends, and they actually collaborating on some projects that handles big data. So then this administration process actually becomes smooth because they are good friends, right? So then I become a part of both sides, physics and computer science. And my physics advisor, who is also affiliated with computer science, it makes even smoother. And at the time, my wife told me that you need to do a PhD degree in CS. I said, how many years? Because he said, if you do it quickly, maybe 2 years is enough. I said, okay, that's a deal. We'll do that. So in total, in 6 years, I just defined it 2 times and I wrote 2 theses and got 2 PhD degrees. That's the
Wow.
story.
Wow.
Yeah.
The research you did for your CS PhD is totally different from what you did in astronomy and astrophysics.
Yeah, it's completely different. So in astrophysics, I do this big data analysis to analyze the properties of dark matter. So we try to use the simulation and try and understand like if we have a different assumptions on the dark matter, for instance, the temperature, etc. So we're gonna have a different outcomes from the simulation. So then we propose a lot of different observer, like something to be observed in the future for future telescopes to do. We don't have this, we cannot test these assumptions yet because we don't have good telescope. But for CS, we are investigating new algorithms. We try to prove the new algorithms that are good from a pure math. And like we need to prove that. We need to assume like there is a computational model, and under this computational model, this algorithm is the best, is optimal, something like that. That's what we do in computer science.
Got it. So
Yeah.
it sounds like your astrophysics work might have been large scale structure simulations or n-body simulations. Is that what you were
Yeah,
doing?
N-body simulation. It's actually we are doing analysis of N-body simulation. So the largest scale N-body simulation is coming from another group. So we do smaller scale because we want to add different assumptions on the dark matter, try to recover some observable structures in the observable universe.
So for the audience, let me just explain that in the early universe, the relatively slow moving matter, so not light or radiation, was mostly this mysterious substance. We still don't know what it is. It's called dark matter, but it is the dark matter characteristics that dominated galaxy and structure formation, clumping of matter in the early universe. And you can study that once you make some assumptions about the properties of the dark matter. You just need to know about sort of classical, not even general relativity, but Newtonian gravity. And then you can study how these things clump together to form galaxies and other large scale structure. There was a time when these were really large scale simulations. So at the sort of cutting edge of the largest simulations that humans were doing. I don't know if that's true anymore, but at one point it was. So it sounds like you've done more large scale computation than any theoretical computer scientist, and you've done more theoretical computer science than any large scale simulator. Is that fair?
Yes, that's true. Yeah. Yeah.
And,
So after
and
that, I went to, go ahead. Yeah.
I was just going to say, so I think you're about to say, I think you did a postdoc at
Yeah.
Princeton. Um,
Yeah.
what I was about to ask you is neither of those two things is that
Yeah.
directly related to machine learning and AI research. So I'm guessing you're
Uh,
about to, well, go ahead. Go ahead. Yeah.
yeah. Theoretical computer science is directly related to what I'm doing at
Okay.
Princeton. Yeah, so we were trying to understand in this for reinforcement learning, right? So I mean, my advisor at the time was Mandy Wang, who is doing reinforcement learning. So we have a competition model. So that is the so-called Markov decision process, which is the underlying model for reinforcement learning, which assumes that the word is a Markov decision process. I mean, maybe I'll add some background to the audience later. Yeah, for that, you can just understand it's a computational model, right? It gives a pretty good modeling for if you do reinforcement learning. So we try to understand under this kind of modeling, what is the optimal you can do, right? So you're gonna learn how to operate optimally in this Markov decision process. What is the best sample complexity? Like if you want to learn a good policy, what is the smallest number of samples you need to take? So this is a purely related to this skill set in theoretical computer science. We just prove a lot of bonds and design new algorithms. So at the time, we actually resolved some open problems in the field. And with that paper, I found a job in UCLA. Yeah,
Great. And
yeah,
you've just been promoted to associate professor at UCLA. So congratulations. You're a tenured.
yeah, yeah. Thank you for that. Yeah, so that's a big relief, actually. Yeah. It
That's
gives me
great.
more freedom to explore other things as well. For instance, this paper that we're going to talk about.
Yes, yes.
Yeah.
I mean, the paper that got me interested in your work
Mm.
is quite different from all the topics that we've discussed so far. And
Yes, that's true.
in a way, it's kind of applied because you're using other people's LLMs and you've built a kind of pipeline that empowers the LLM to do amazing things.
That's true.
Um, so tell me how you got interested in this problem. Just what was the process?
Yeah. So actually, like I said, I have this mathematical background. I do prove myself, everything, right? So I'm pretty interested in this deep math problems. So Yichun Huang, who the first author of this paper, we came from the same undergrad program. He's now an independent researcher, and he got enough money. He don't want to work for someone. He's also super interested in this math problem. So we started to chat about. I mean, he's always doing physics, and unlike me, I'm doing computer science. But he's pretty interested in this new AI stuff, and he reached out to me that maybe we can work on something together that's interesting in our both domains. So back like at the beginning of the year, we started to chat about the problems. Like he was doing both IPHO, like the physics Olympiad, and MO while he was a high school student. I just got into a little bit because in my province there's no such culture. It's a very poor province. I just know a little bit of that thing. Yeah.
Just for the audience, so
Mhm.
IPHO is the International Physics Olympiad, and IMO is the International Mathematics Olympiad. And both of
Yeah.
them, to make the national team or make the provincial team, you have to be extremely capable. And
Yeah.
the problems are extremely hard. So ordinary people can solve basically zero of the IMO problems.
Yeah. That's true.
So so go ahead. Sorry to interrupt you.
Yeah, it's okay. Yeah, so we started Chatbot, right? So we have these new AI tools, right? So how can we solve that? I mean, in the beginning, I was suggesting maybe we should use our reinforcement learning algorithms that we have investigated for such a long time. But it turns out it would be very difficult to run reinforcement learning on these big models if you don't have infrastructure to them, right? So then we just think about think about if you have a reinforcement algorithm, so you run this algorithm. In the end, what do you get, right? So maybe you will just have some policies. The policy will operate on these big models. So we're saying, okay, maybe we just design our own agent without using reinforcement learning algorithm but use like human reinforcement learning. So we do reinforcement learning using our brain to design this policy.
Yeah.
So yeah, so that's how we got started, and we try on this existing IMO problems with different agent, with different and majority we doing these things on this Google AI Studio. Thanks to them, that's for free, and if you do that manually, so we have done a lot of research on that, and eventually got some good result. And then this IMO, a new IMO data set comes out, right? So we say maybe we'll try on this, and then we try that. Got some very good results, and then Google and OpenAI published their results saying that they get IMO gold medal. I said, oh, we actually get that too without having a new model. So we're
Right.
just rushing out for the new paper at the time. Mm,
Good. So
Yeah.
so let me just recap a little bit for the audience. So every year, some of the smartest high school age kids in the world get together in one place and they compete to solve, I believe is it six problems
Yeah.
each time? And they have, how long is it? 90 minutes per problem?
So every day it's 4 hours. It's two
Okay.
days. Yeah. Each day is three problems.
Yeah. Okay. So they have a
Yeah.
little more than an hour per problem, and these are
Yeah.
extremely hard problems. And each year, the people who run the competition are trying to design new problems that are not like the old problems that are in this, the material that the students have studied. And so if those committees do their job properly, it gives you a de novo set of challenging tasks for your AI, which admittedly the problems could be somewhat similar. The solution techniques typically are similar to solution techniques that have been used in the past, but the new problems are hopefully qualitatively different than
Yeah.
what the AI model has seen in its training data. And
Yeah.
so Lin and his collaborator were able to build a pipeline. I think the first thing you published was with Gemini, but you've since updated it. You've got it working with, I believe, Grok, and also, is it GPT-5?
GPT-5, yes. Yeah,
So
we
basically,
tried these three models. Yeah.
yeah. So three of the most widely used models now can be used off the shelf using your pipeline. And I'll let you describe how your pipeline works in a moment, but using this pipeline to solve IMO problems at the gold medalist level. So tell us how your pipeline works.
Yeah, of course, of course. Yeah, so in the beginning, right, so we're trying to use FinSense Gemini Pro that's available for everyone in AI Studio. And we use that to solve the problem. So we're trying, like, what is the most intuitive way to ask the model to solve the problem? Would be something like, okay, try all possible method on this problem, right? So we find there is actually it's very useful for this feedback of the model. It tells you like what are the steps that if you're thinking about. So you look at this process. At that point, it's gonna fail because there is a reasoning budget. So in terms of the large language model context, there's something called context length, right? So the model can only handle a certain length of a window of tokens. So if the reasoning process takes up all this reasoning budget, it's gonna fail. So basically, what it means is that it cannot search for other method. It does not have enough space for that purpose. So because of that, we have to use some framework to handle this issue. That's a starting point. So what we do is that, okay, maybe we don't do this difficult, right? So, okay, so you start with your initial solution. I don't ask you to try all possible solutions now. You just stick to one method, one possible method, and get an initial solution first. Okay, so that's actually the first step. Once you get the first solution, it might be incorrect. I just say, okay, give you a chance to do refinement. So this all prompts. Okay, so the solution is coming from the language model. So got the solution, you add another prompt saying that, okay, now here is your solution, your previous solution. Now you have one step to refine that and tell me your new solution. Okay, so that way you get the new solution. So this is the initial step of getting the starting point of solving a problem. Okay, so remember, every prompt has nothing to do with the problem itself. It's problem agnostic. Okay, so now we would go into this so-called verification and refinement process. And so with the initial solution, now we have this so-called verification prompt saying that, okay, so now somebody gives you a solution. Now you are a reader, so tell the language model. So find every bug in this solution. Okay, if you don't find any big major justification gap or something like that, you just say this solution is correct. Okay, otherwise give me a bug list. So that's the verification step. Once we get this bug list, right? So you may say that, okay, this solution is perfect, or it says that, okay, there's a bug, there's multiple bugs. This is the list. So if we have the list of bugs, we just ask the language model to do it to correct the previous solution. Okay, so we gotta do this bug list here, and here use your previous solution. Try to fix the bug list and refine your solution. So that's the refinement step. Okay. So again, the verification and refinement step. So now you will get the new solution. So we'll ask the verifier to do the same thing. So if the verifier says that, okay, the solution is perfect, so we will ask the verifier to do it again. So the language model, there is a properties. Actually, it's called the property is called temperature in the model. So because of the temperature, actually, every time we ask it to give you something, it's always randomized. It's never deterministic. So even though it previously says the solution is perfect, next time you ask it, it may be incorrect again. So we will just, whenever we see a correct solution coming from the verifier, so we will ask it to verify it again, verify it again, verify it again, until 5 times we get all correct solutions. We'll just say, okay, now I'm going to accept this solution and output that. And on the other hand, if the verifier says that this solution is incorrect, there's a bug, there's a major justification gap, something like that, and we ask it to correct, to refine, right? So if it happens 10 times, that means the model is training on solving this problem. We just output fail. Okay, so that's the entire process. So to summarize, right, in the end, the process will either output fail, okay, so I cannot solve the problem, or a solution that it itself believes it's correct and perfect.
Quick question. So the verifier finds gaps in the proof.
Yeah.
But does the verifier ever suggest a different method of attack or a different methodology to solve the problem? Does that ever happen?
We specifically ask the verifier to not do that.
Okay.
Just find the gaps. Don't do any solve or whatever. The reason is the same, because the budget of reasoning is limited. We don't want the budget to be spending on irrelevant things.
Okay, but
yeah,
well, the refinement part, the refinement module, will it sometimes shift gears completely and try a different attack?
Sometimes you will. Sometimes you will. Yeah, because we see we run a bunch of a lot of experiments. We see sometimes it happens. Things like, okay, my previous solution was incorrect. I will try a completely new approach. Yeah.
And what is the typical number of tokens that you're expending in one of these processes?
So actually, we had that in the paper. Let me just to be precise, maybe I can look at those.
Yes, I should have looked this up before I got on, but
well, it's okay. It's okay. Yeah. Yeah, but I can tell you that typically it's 300. I think it's No. So like the 20K each per step. So
Okay.
the verification takes about every time it's random, like I said. Typically, it goes up to 10 runs or 12 runs, something like that.
So it's less
Yeah.
than a million. It's less than a million tokens to solve an IMO problem.
Yeah, sometimes it's less than, but sometimes you into this very bad loop. It keeps going until the end. It gives you the solution.
Okay,
And
but
sometimes even like we have an upper limit. Like if it goes 30 runs, we just say that I'm not gonna try anymore.
okay,
Like sometimes we run 30 runs and never find a solution.
okay. But the
Yeah.
total cost, you're talking about maybe tens of dollars at most for the whole thing, like for all six problems,
If you're lucky.
not more than hundreds of dollars.
No. But the experiment takes about $1,000. Like for the whole experiment, it takes about $1,000. Yeah.
Okay, I'm just trying to get order of magnitude for the
Yeah.
audience. So after I read your paper, then at
Yeah.
one point there was actually a nice podcast. I think it was done by Andreessen Horowitz, where they
Mm,
interviewed the team leaders who did the IMO, led the IMO problem solving for OpenAI. They also revealed their process that they actually they claim had not modified the model very much
I see.
for. They had also used a pipeline, which was, I think, not that dissimilar from yours.
Yeah.
Um,
Yeah, of
so,
course.
but when I first read your paper, what got me excited is I've always had the feeling that the pre-trained models already have just tremendous capabilities because they've
Yeah.
seen so many solutions of problems.
Yeah.
So, and things like RL and chain of thought are really just to kind of elicit that capability that's sort of latent in the pre-trained model. And I thought
Yeah.
your paper was a very good demonstration of that.
Yeah.
And I think for tasks which aren't math or proving theorems, just even like reading a document the right way and extracting the right information, I think also if you had this kind of, verify, refine pipeline, and you're willing to expend enough tokens, you can do expert level work. You can make them,
That's true.
even though it's only an off the shelf model.
Yeah.
What do you think about that?
Yeah, that's really true. I mean, including writing some papers, I want to refine the papers. I do use the similar framework to ask it. I try to refine and try to give me a verification list and find the problems and then do the refinement again. So that really improves the capability. The agentic framework here is really helping to resolve this context, the reasoning boundary problem, right? So if the model itself does not have the capability, it will not work. I mean, you run this agentic framework with some of the open source models, it's not giving you the same performance. It really depends on the underlying model's performance. It needs to reach some kind of capability level, right? So then this amplification will work. Otherwise, it doesn't work. It's something like in probability theory, there's something called probability amplification. So, for instance, if you can answer a question with probability greater than half, oh, actually, you don't need to be greater than half. Because notice you can tell me that your solution is incorrect or not, right? I can amplify that probability to be 100%, but just
Yes.
repeatedly run the thing. Yeah.
Yes.
So it's
It's
something similar to that. Yeah.
like noise suppression. Like it,
Yeah. Exactly. Yeah.
yeah, so incredible. I know of some examples in industry where
Mm.
people have built pipelines that are a little bit like yours, where they just are willing to expend a lot of tokens, but the tokens overall in aggregate still cost less than paying a human to do the task.
Yeah.
And actually, my startup built stuff like this to analyze legal contracts and things like this
Mm.
and financial documents. And it can get to a point where it's sort of 98, 99% able to extract really complicated things from a very complicated contract or financial document, but through this process where it has a verifier refiner kind of chain.
Yeah.
But it's still cheaper than having humans do it.
Yeah, of
So,
course. Of course. And humans can make a lot of more mistakes, I think, without this verification, right? Humans, they also need verification.
yes.
Yes.
If you take the chain of thought traces that are
Mm.
generated say for
mm,
this 2025 IMO,
mm,
and your model solved the 5 problems that it solved.
mm.
Way to make it introspect and ask, like, have you seen a similar problem that used these same methods or tricks in your in your memory, or like here's a question, like, is the space
Yeah.
of techniques used to solve the 5 problems, um is it finite enough that basically that whole space is kind of covered by some kind of mesh of all the things the model has been trained on? Is there any way to approach that kind of question?
So if I understand correctly, you were saying whether this model tried out a different process, right, for this problem.
Yes.
I believe it's not, because like initially I mentioned that if I add a prompt and try out different method, right, so for this problem, it's going to fail. Okay, it's gonna use out the reasoning pretty soon. But we ask it to give an initial solution, and that solution, the assumption of the initial solution is that it's on the correct path.
Hmm.
But sometimes it's never going to correct the solution to be the final correct solution because it got into the wrong path.
Hmm.
Okay, so that's why we got this 30 runs. It's all fail,
Yeah.
and so it really relies on the initial sampling and it makes it correct. So somehow we can understand like this: if the model capability is very strong, the initial solution is already on the correct path with higher probability than other models. If it never gets any correctness in the initial solution, like the refinement process will be very difficult to make the eventually correct.
Okay.
Yeah,
So for problem 6, which was by far the hardest problem
yeah,
in 2025 competition,
yeah.
what can you conclude about the reasoning traces for your model on problem 6? It just didn't go in the right direction even from the beginning?
The problem six, it's not correct because if I remember correctly, there are two reasons. The first is that the verifier says that it's correct, but it's an incorrect solution.
Okay, so the problem was at the
Yeah,
pair. Yeah, okay.
yeah. The verifier is not strong enough to identify the even issue there. And the second instance that it reports failure is that it really cannot find a solution.
Hmm.
It tries out the different solutions, and that verifier always says that it's wrong, it's wrong. But in all the cases that we got the final outcome, and it's always saying that the solution is correct, but it's actually not correct.
I see.
Yeah, it's reporting a naive upper bound, and then the lower bound is saying that this is actually the lower bound, but it's not correct.
Right.
Yeah, some theorem they're using and it's not really true, and the verifier didn't locate that, or even the RSR locates the error, but the server cannot solve it anymore.
Got it.
Yeah,
Got it. So, for me, I'm already using the models for frontier research in
yeah,
theoretical, and I find them extremely useful
yeah,
as tools because they've read more or less the whole archive, or they can quickly read if they haven't already trained on a particular paper, if they find it in the search, read it
yeah,
quickly.
yeah,
Uh,
yeah.
and I've actually been working with one of the big labs on a project to try to understand how well the model is helping research scientists. And
Interesting.
yeah, I think it's really at the point now where I can imagine the whole community of academic scientists starting to use these models the way that like physicists would use Mathematica 10 years ago. Everybody uses Mathematica or MATLAB to some
Yeah,
degree to do some algebra or do some integral that's complicated. But I think it will become just a standard tool for everybody's research. And
that's true.
I actually think so. We have in this project that I'm involved in, we have several candidate results from the models, which are publishable new kind of ideas and how computations that
Yeah,
if we publish that paper, the model should be a co-author. Actually,
yeah,
as like say one of my PhD students or postdocs would be a co-author. So
yeah.
yeah, so I think we're really right on the verge of that. I'm curious what you think.
Yeah, that's a great idea, right? I'm actually trying to do that. So actually, it works. Pretty well. So when I write down some theoretical papers, so when I wanted this model to tell me the proof, it gives me a very good proof pretty quickly. So I just write down the theorem and try to prove it. It gives a very good proof very quickly. Yeah. So for now, it's not at the level it's already a core there, but I see the path. It's already there. So actually, we are trying to we have a new project. I'm starting a new collaboration with some professors in the math, not UCLA math, but there's some other places. We're trying to build a company for for mathematical researchers, right? So you just ask the model, and it gives you the proof, and it will give you directions. And I mean, even without the anything, like that's already very useful, right? So you just ask them like GPT-5, it gives a pretty good hint, for many problems.
Right.
Yeah.
By the way, I forgot to mention earlier when we were discussing the IMO situation, I think ByteDance,
Yeah.
you're silver medal level, but they had incorporated Lean, which is a
That's
tier
true.
improvement. Which
Yeah.
they had an LLM coupled to Lean,
Yeah.
and that thing performed kind of at the silver
Yeah. Yeah.
medal. That's
Right.
another. In your case, it was 100% large language model, no theorem proving
No
axiom.
symptom. That's true.
Exactly. Yeah.
Yeah. So they using the new proof. That's another hybrid approach, right? So they say, okay, I have a solution for the model, then you convert it to the new proof. So then the new verifier directly verifies it, and then you refine that. It's a different approach. Yeah.
Yeah.
In some sense, it's going to be more scalable. I mean, if the model has larger capability, because you immediately know whether the solution is correct or not. But because of the mean proof, right, it's already complicated. So then they require a lot of computation power to achieve this. So unlike us, right, so we just less than several dollars, right, several bucks per problem. So they maybe need a lot of lot computation time to handle even one problem.
Yeah, I think that
Mm,
my guess is that the language models are and the methods for using them, like yours, are
mm,
going to improve to the point where there will be some specialist mathematicians who still want to use Lean, but the general utility of these language models is so high that
yeah.
I think it will become an everyday tool that every researcher is using all the time.
That's true. That's true. Yeah, at some point, maybe graduate student they cannot they cannot find a job in research labs anymore.
Yeah, well, it's funny. Just before I got on the
Mm,
call with you, I was talking to one of my research collaborators,
yeah.
and I told him that about some recent results I got from the model, and I said, "This is like having your dream grad student, where
Yeah.
you know never sleeps. He's super
Yeah.
fast, reads the
Yeah.
whole, and he can calculate things very well. So yeah, it's actually incredible."
Yeah. That's true. Yeah.
Tell us a little bit about your research plans. It sounds like you're more of originally more of a theoretical computer scientist, right? Are you getting
Yeah. That's true.
pulled into AI more and more?
Yes, yeah, that's what I'm actually into this agentic AI research more recently, trying to use agentic AI on different applications, right? For instance, this MO. So there's a follow-up. We're trying to make this IP actual, right? So physics Olympia. Make the point. I mean, so actually, you know that it more relies on your knowledge rather than this reasoning capability, right? So, but
Yeah.
recently, some results reporting that they achieved gold medal, but without full marks. We want to see that actually you can use language model to solve all these problems 100% without any gaps. I mean, except for these experiments, the models cannot do experiments right now.
Of course. Yeah.
Yeah, for all the theory questions, they should achieve 100 marks rather than giving any like mistakes, because it's more reliant on the knowledge, and the models have all the knowledge to solve them.
Right.
Yeah, that's a one follow up. Yeah, the other follow ups. Right, so one thing very interesting to us is like uh, so we're solving problems. Can it be used to propose problems? Yeah, so that's also related to like can AI models be used to propose sensible research questions, right? So
Yeah.
research open questions. So if that is the case, then it can self-propose and solve, and then that's a flywheel, and it's gonna be a big contribution to the entire research community, I would
Yeah.
think.
I,
Yeah.
I think the answer to that question is definitely yes, because
Mm.
as I mentioned, projects that I'm working on, involving some of the big labs,
Yeah.
uh, part of it is to use the thing to do computations or solve well-posed problems, but part of it is not. Part of it is for the model to ideate, to
Yeah.
come up with creative connections or suggest new ideas or new directions. And it's actually quite good at that. That part is less surprising to me than
Yeah.
the fact that reliably prove, because the IMO problems, it's not just you give the numerical answer, it has to actually
Yeah.
deliver a tight proof. That's the most surprising to me, is it can deliver a very tight proof that's correct.
Yeah.
The idea that it can say, oh, have you read this set of papers? They seem connected to this idea, and maybe you should, consider this new research direction, which joins these two things. That
Mm.
seems really plausible to me, that the model could do that. I think, to me, proofs seem harder than that.
Frozen. Yeah, but on the other hand, right? So if you want to propose the good IMO question, it's not easy. Yeah, so it
Right. So
needs to be correct the difficulty, right? So it
yeah,
cannot be too difficult,
yeah.
cannot be too easy. Yeah.
I think someone who's skeptical of the IMO in general,
Hmm.
either as a filter for human talent or as a test for models, I think the skeptical statement is something like this:
Hmm.
the space of IMO, of Olympiad problems, is very constrained, because it has to be something that the kid has enough background to solve this problem. It can be
Yeah.
solved an hour roughly, and
Yeah. Yeah.
very well posed, right? And so then
Yeah.
that sort of brings you into of course, to do these things, you have to be very capable, have very special talents, but still,
That's true.
it's a very small subspace of the space of all mathematical thought.
That's true.
And
That's true.
so
Yeah.
the question is, how representative is this little confined subspace to its ability to do like broader math research? I think that's still somewhat unanswered.
I don't believe that it's like capability of some MO is the representation of general
Yeah,
capability. No, no. And that search space has to be small enough for the kids to solve them. Yeah.
yeah,
Yeah.
exactly.
Mm.
But still, but like with the tool Mathematica,
Mm.
it can't do everything. But if I can get it, if I can get my research, if my research is stuck on something that's pretty well posed,
Yeah.
then I can have the model beat on it and get somewhere where maybe it would have taken me 6 months or 6 weeks to do that, but the model can do it very quickly. Then that's still worth a lot, I think.
Yeah, that's true. Yeah. Actually, my one of my courses, who wrote a paper, but not with me. So they had called this Grok project, right? So he was from theoretical computer science as well. He has some open problems. So he write papers. He just made the AI to do them. Like the AI, if I remember correctly, solved several of the problems. They reported that in the archive paper recently.
Yeah,
Yeah,
yeah.
very
So
interesting. Yeah.
I think we'll see more and more results like that in the next couple of years, for sure.
Yeah, that's true. That's true. Yeah.
Yeah. Great. Well, let
Mhm.
me ask you to speculate, since you're a professor of computer science, and
Yeah.
you've done some amazing work with LLMs.
Mm.
How far are we from AGI?
Oh, that's
And
good.
can what if we stick just with transformers, how far can we get?
I have no idea how to answer this question correctly. Um, to me, with transformers unknown, I don't think it's gonna achieve AGI. You have to combine that with other frameworks. Right? For instance, agentic framework might be a direction that makes AGI closer. But still, I don't think we are closer to that yet. So even for now, right? So you have the organic thing and everything. You can do amazing things, but sometimes you can make stupid mistakes. And I don't know. For human beings, you wouldn't make those mistakes, right? Even for this so that's a different domain. Like you do self driving, right? So Tesla, I drive a Tesla, like the self-driving capabilities is amazing, but sometimes it just makes stupid mistakes. I have to I have to intertwine. Yeah, it's a so that's like for this little things, right? So it's all related. Like human beings, like our knowledge is connected. They make reasoning based on the Intel memory and Intel context, and also can update the brain very quickly, right? So today you learn something, tomorrow it's written in your own memory. So there's for this LLM, right? So you need to wait for the next round to be trained, right? So even you use the agentic framework that can have a long-term memory, but it's stored in the database, right? So that actually, if you make an analog, right, and compare to human beings, that thing is like the short-term memory in human brain.
Yes.
So yeah, so we get the human brains get trained right on the short-term memory while you're sleeping, right? The next day you get refreshed brain. But the language model is completely different. Maybe in the future we can make it working better, but right now I don't know yet.
Yeah. That's the
Mm,
basic problem is that,
right.
I can, if I'm talking to a graduate student and he's confused about something, I can update him very quickly. I can just write a
Yeah,
few equations and then all of a sudden his thinking is transformed by that. But for the
yeah,
models, you do an entire pre-training run to modify the weights and do all these things. We don't have another layer or module that can update the way my graduate student can update.
that's
So
true. That's true. Yeah.
I think that's something people should work on, but it may involve a better architecture, different architecture than transformers. I don't know.
That's true. Yeah, but still, transformers are amazing. And you just like also it works. You just predict the next token. How
Yeah,
come it has reasoning ability? It's so amazing. Yeah,
yeah,
that's actually a good research question. Right? So I try to understand why this thing makes it like has the reasoning ability, right? So is
yeah,
it really have reasoning ability or just mimicking something? Right? So it's
yeah.
just illusion. I don't know. Yeah,
Well, probably you're familiar with this debate is raging in the on the archive or in the CS literature that
yeah,
does it actually reason or does it simulate strings of text that humans would generate if they were reasoning, right?
yeah, yeah. That's sure. Yeah,
Number two still might be good enough, right? To do a lot of
that's true.
useful
Yeah,
stuff. So
that's true. That's true. Yeah. Yeah, I believe it's the second case. Like my belief will be that
yeah,
because it is token prediction. Yeah.
yeah, I think there have been clever experiments to see whether it is actually capable of abstract reasoning, and in fact, it's not.
Mm,
You can build things. I think one clever paper I saw, you probably saw this paper, where
mm,
they use very obscure computer programming languages where the
mm,
syntax, it's unlikely to have ever seen this syntax in its training data.
mm.
And then they ask it to just perform some simple thing like a sort or just standard task, but it literally can't do it because it's never seen strings of
This.
tokens.
Yeah, I see. Yeah,
So
yeah,
um,
yeah,
in terms of the amount of reasoning required is very low, but it just
yeah.
can't do it in this
So
obscure.
the analog, right? The analog capability is not there.
Yes.
I
Yeah.
guess. Yeah. Yeah, that
But
probably is cannot be solved by transform architecture. That's my conjecture. Maybe it can solve. I don't know. Just it's a attention mechanism. It does not encode this kind of behavior.
yeah.
Right? Maybe. Yeah.
Yeah. Good. Well, I appreciate your joining me. I know that I want to congratulate you because you just had a new child join your family. So
Yeah.
you must be short on sleep. I really appreciate that you were able to get on this
Yeah.
uh, episode with me. Um,
Yeah.
any final thoughts on any non-obvious things about AI or the future of machine intelligence that you want to share with the audience?
It's not obvious.
Well, maybe
Now,
not obvious to the average person, but something that maybe you find interesting.
okay. So, and maybe not necessarily interesting, like you said, right? So, probably like currently, we're saying that AGI is close, right? Maybe that is just a happening things, right? Maybe it's not there yet. We really need the new architecture, for instance, making better architecture than transform. And one thing that I'm sure is that transformer it cannot compare to human brain because it's too energy consuming, right? So it uses too much energy to do training, to do reasoning, whatever, and not real reasoning. Maybe it's just mimicking reasoning. And But human brain uses so less energy, can still do so much tasks, right? So many different tasks, so efficiently. So can we achieve the same thing? Use a different architecture, whatever, right? So that if that day comes, right, we have a very efficient AI. So then I'm not sure what will happen, right? So maybe let's make some assumptions, right? So then the GPU market may crash, right? So that would be an issue. I don't know.
Yeah.
Anything can happen in next 2 years or 3 years, right? I don't know.
Great. Yeah, it's super
Yeah.
exciting. Well,
Yeah.
want to congratulate you again on your interesting paper and your new child.
Yeah.
And
Thank you so much. Yeah.
yeah, and we can have you back on the show in the future to talk about some other work.
Yeah, of course. Thank you. Thank you again for the invitation. It's my great honor to be here.